So let's see what it looks like. So scientific notation is just a way of writing numbers that have a lot of decimal places or a lot of zeros. So in other words, really big numbers in a convenient manner that tells you, does a good job of telling you how big the numbers are. So for instance, let's say I wanted to write the number 186,000. I believe that is the number of miles per second that light travels. Now, that's not that huge a number, right? I just want to use this as an example. So what we can do is, instead of thinking of this as 186,000, I'm going to think of it as 1.86 100,000s. Right. So what we're doing here is we're using this number to tell us the general size of the number, and this number to tell us how many of those we've got, essentially. This is called an order of, or powers of 10 are called orders of magnitude. So we would say that this this had, well, we'll see in just a second, but this is 5 orders of magnitude. Because we're not going to write this 100,000 as 100,000. We're going to write it as 10 to the 5th. We're going to say this is 1.86 times 10 to the 5th power. And that way, we don't have to write all the zeros. And not only that, the really nice thing is this number, we can read off how many zeros something has, which you might say to yourself, 5 is not very big. I can count to 5. However, when you have a number that looks like this, let's say 508, and then put some zeros here. Right? When you're doing science, sometimes numbers like this show up, and they're just really huge. And so it's much easier to compare 5.28 times 10 to some power. What do we have? 3, 6, 9, 12, 13. 10 to the 13th. And then I don't have to count the zeros. I can actually see how many there are from the exponent. Right? So this is telling me I have about 5 of these 10 to the 13ths. Right? So I'm counting in 10 to the 13ths. I have about 5. This is super convenient for numbers that are huge like this, and this is by far, or this is by no means, the largest number you'll ever see in science. There's all kinds of numbers bigger than this, and also smaller, like much, much smaller. You know, when you start talking about cosmic distances, right? Like you start measuring in 10 to the 13th or 10 to the 25th or whatever meters, right? And you don't want to have to like look at something with 25 zeros. That's terrible. What you want to do is look at something like this, where you say 5, and then it's got 13 orders of magnitude. Similarly, you can do the same thing for very small numbers, right? Numbers that have a lot of decimal places. 0.00000000175. Let's do that one. Except I want to think of this as 1.75. 1.75 times 10 to, now I want to say how many decimal places we have. And remember, the way this means that we are multiplying by 10 13 times. Well, that means we're moving the decimal place to the right 13 times. So I move this decimal to the right 13 times. Well, this 1.75, I would need to move the decimal place to the left. Let's see, 1, 2, 3, 4, 5, 6, 7, 8 times to get to where it actually is. So that's like dividing by 10 8 times. When I move the decimal place to the left, that's like dividing by 10. So this is 1.75 times 10 to the negative 8. And in this way, we can identify how big a number is without having to count the zeros every time, because we're like literally writing out how many zeros or how many decimal places it's got, or how many places after we would move this decimal to the right. to get to, or to put it in the right spot. And that's what scientific notation is. That's all it is it's a way of writing numbers in a convenient fashion, so you don't have to look at all these zeros and count them every time. You can just read off the power of 10 to tell you how many zeros there are. Now a couple of minor points here. You might say something like, well, okay, this 5.28 times 10 to the 13th, couldn't I write that as 528 times 10 to the 11th? And you absolutely could write this or write this number like that, because it is, right? If I take this 528 here and I move this decimal 11 places to the right, well, that would give me this same number. However, scientific notation is always one digit here. So you always have one digit before the decimal place. That's why I wrote this as 1.75 instead of like 0.175 or 17.5. You always, like, the first non-zero digit goes after the decimal, and everything else goes later than that. Yeah, boy, I said that really awkwardly. The thing I'm trying to say is this number right here is always between negative 10 and 10. So you're going to have, like, you're never going to use two digits here. It's always exactly one digit. Sometimes it gets a little bit awkward and you end up having to convert your scientific notation or convert your calculation into official scientific notation, which I'll show you right now. So one of the other nice things about scientific notation is that it makes calculations relatively simple with these huge numbers by essentially keeping track of the decimal places for you in the following way. Let's do an example. So let's say I want to do 3.6 times 10 to the 15th power divided by 9 times 10 to the 11th power. Right? If I were to write this all out, it would be a giant mess because I'd have, what, 26 zeros. I don't want to deal with that. Luckily, we don't have to. So all I'm going to do is this. I'm going to write this as 3.6 over 9 times 10 to the 15th over 10 to the 11th. And we're just going to use rules of exponents to cancel things. 10 to the 15th and 10 to the 11th, well, we have 15 tens in the top, 11 tens in the bottom, and 11 of them are going to cancel, leaving us 4 tens in the top. 10 to the 4th, and then over 1. 3.6 over 9, you can just jam that. You can just jam that into a calculator. You can also notice that 9 goes into 36 4 times, so this is 0.4. So this is going to be 0.4 times 10 to the 4th. Now, that is not official scientific notation because this 4, like, this needs to be a number between 1 and 9, right? So I don't want to use 0.4. I want it to be 4 point something. So the way you want to think of this is it's a trick that I've used a bunch of times already when I was multiplying, right? So let's say I have 80, or what do I say here? 25 times 80%, right? And I said, actually, is this exactly how I said it? It's not exactly how I said it. Let me try this again. Sorry, I'm going to redo that with a better example. So let's say I have 2.5 times 800. A thing that I can do to make this a little bit easier is I can move this decimal place 1 here and this 1 there, and now I've got 25 times 80, which is actually a little bit easier, right? Because 25 is a quarter of 100, and so if I need 4 25s to make 100, and 4 goes into 80 20 times, so this is 2000 or 2000. But that's made easier by the fact that I can adjust the decimal places, and that's the same thing I can do here. I really want to make this 4, right, by moving that this way. So I need to move the decimal place to the left, make it smaller here. I don't know if that helped. Let me show you what I'm talking about here. I'm going to rewrite this in the following way. This is 0.4 times 10 to the 4th is 1 followed by 4 zeros. Right, it's 10,000. I can move the decimal place here that direction by doing this, right? In the same way that I did it down here. So this is really 4 times 1,000, or 10 to the third. That's not a very pretty 3. Let's try it again. A little neater this time. And so the idea here is I made this 0.4 bigger by a factor of 10. So to compensate, I have to make this 10 to the 4th smaller by a factor of 10. So I'm going to put this. So that's the essential idea of dividing numbers when you have scientific notation. We can also do the same thing with multiplication in a very similar and also equally convenient way, perhaps even more so. If I have, let's say, 1.5 times 10 to the 16th power times 4 times 10 to the negative 11th power, right? So let's say I've got those things. Keeping track of all this, keeping track of all these decimal places would be a mess, right? This would be 1, 5 followed by 15 zeros. That's not a number I want to deal with. Similarly, this would be 0.00011 times 4. I don't want to deal with that either. What's much easier to do is to rearrange this in the following way. I can do 1.5 times 4 times 10 to the 16th times 10 to the minus 11. Why is this easier? Because the rules of exponents. Rules of exponents tell us what that's going to be. I'm multiplying like bases, so I'm going to add the exponents and get 5. 1.5 times 4 is 6, so I get 6 times 10 to the 5, and I'm done. I didn't have to keep track of all the decimal places myself. I just let the rules of exponents do it for me. And that is what scientific notation is for. It's for writing numbers in a nice, neat fashion so that you don't have to count all the zeros to get a good sense of how big it is, right? You can just read off the number of zeros by looking at the exponent. And it lets you make calculations with those numbers easier by keeping track of all the decimal places for you. That's really what a power of 10 is it's a decimal place. I don't know if maybe that's not obvious to people, right? If I take, let's say, 3.56 times 10, what I'm really doing there is I'm going to get 35.6. And all I'm doing when I multiply by 10 is I'm sliding the decimal over 1. Let's say instead I multiplied by 100. I'm going to slide the decimal over 2, right? And I'll get the 356. If I multiply by 1,000, I'm going to slide the decimal over 3. If I divide by some power of 10, I'm going to the left instead of the right. And so 1 decimal place equals 1 power of 10. And so that's what scientific notation keeps track of for you. It's really just keeping track of the decimal places for you. And you use rules of exponents to handle them rather than like doing some giant multiplication chart that's got 400 zeros in it, right? That's such a waste of time. It's way easier to let scientific notation or let your notation handle all that for you. Very convenient. That's really all I want to say about scientific notation. There's not much else to it. It's really just the two things. Like I said, it's a nice convenient way to write stuff that gives you a sense of the order of magnitude of that number without you having to count a bunch of zeros. And it lets you do calculations easily by keeping track of the decimals for you. And that's really all it is. So that's where I want to stop the video. All right, great. That's a nice short one, and I guess I will see you guys in the next video.